Okay, so we're up to chapter 4 of Routing and Switching Essentials, which is an introduction into switched networks. So we'll look at LAN design to start with. So we'll explain how switch networks support small to medium-sized businesses. We'll talk about how data, voice, and video are converged into a switch network, and we'll look at a switch network and describe a switch network in a small to medium-sized business. And then we'll look at the switched environment. So we'll look at how layer 2 switches forward data in a small LAN, and we'll look at how frames are forwarded in a switch and compare how a collision domain to a broadcast domain. Okay, so LAN design. So networks have been getting more and more complex as time goes by because we do more and more with them. And so next generation networks need to be secure, reliable, and highly available. They must support a globalized workforce, and no time better than at the moment. And they must be able to integrate legacy devices as well. And so a converged network basically means we have everything going over the one network. And so 20 years ago, you'd have a data network, you'd have a phone network, and you'd have a video network. So all different, all with different technologies. And so you've often had to have 3 different support teams to do that. And so basically now that we have everything converged, everything over data networks, you just need one support team and all the traffic can go through the one network. So, bit of marketing. Cisco Borderless Network has the following features. It allows organizations to connect anyone, anywhere, anytime on any device, securely, reliably, and seamlessly. Provides the framework to unify wired and wireless access, including policy, access control, and performance management across many different device types, and provides network services and user and endpoint services that are all managed by an integrated management solution. And so that's just some of the products that they market. And so the borderless switch network design guidelines are based on the following principles. So you have a hierarchical design, which facilitates understanding the role of each device at each tier. Modularity allows seamless network expansion and integrated services. You've got resiliency, so basically it's always available, and flexibility allows intelligent traffic load sharing. The 3 tiers of the hierarchical model are access, distribution, and core layers. And so access layer, of course, is down the bottom here. That's where all the hosts gain access to the network. Distribution are either routers or layer 3 switches, so they make forwarding decisions where the traffic needs to go. And the core layer is all about moving that data quickly about. So pretty much. Anyway, so distribution layer basically interfaces between the access layer and the core layer, and it aggregates layer 2 broadcast domains and layer 3 routing boundaries. It provides intelligent switching, routing, and network access policy functions to access the rest of the network. So in the distribution layer, you would also have your access control list there to provide security. The access layer is pretty much as I said before, and the core layer is the network backbone. It provides fault isolation and high-speed backbone connectivity. So you certainly want redundancy, and especially in distribution and core layers. But yeah, and so smaller networks that do not need a separate distribution core layer can use a 2-tier campus or collapsed core network design. So yeah. Okay, so a role of switch network. And so a hierarchical switched LAN allows more flexibility, traffic management, and additional features. So you can manage quality of service, you can have additional security, you can support wireless networking and connectivity, and you can support new technologies. Okay, so form factors of switches, and so down the bottom of the stack, I suppose, are fixed configuration switches, like what's in our rack, and so basically you can't change much about them. If you need different functionality, you'll probably need to buy a different switch, and so the other end of the scale is a modular switches, and so with those, as you can see, they often have redundant power supplies and they have all these extra expansion slots so that you can change the functionality of that switch by just adding extra cards to it. And so that's certainly the most flexible solution there, but of course it's also more expensive. And then there's sort of a cross between the two where you have a stackable configuration. And so basically, we're looking at the back end of the switch, not the front like we are the fixed ones. And so you can basically plug the back plane of these individual switches and turn them into one switch. So as you can see, it goes from that one to 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 that one, and then that one loops that, and so you've made a circular backplane, but that's shared between all the switches. And so you actually manage that as a single switch, and so you use a modular numbering system to actually configure individual ports and the like. And so that is certainly a good flexible solution. So choosing switches, of course, there's a whole pile of considerations, and so of course how much you can afford is one thing. What port density do you want on the switches? What power is available? What reliability you require? What speeds you require? What size buffering is available? And also how scalable the network is, so allowing for growth, of course. Now, the switched environment. So switching is a general concept in networking and telecommunications. So a LAN switch makes decisions based on two criteria: the ingress port where the frame enters the device, and the destination MAC address if we're talking about Ethernet especially. A LAN switch maintains a table that it uses to determine how to forward traffic. So the router has a routing table, the switch actually has a switch or MAC address table. And so in the diagram, if a message enters the switch on port 1 with the destination address of EA, then the switch forwards the traffic out of port 4. And so by that, we look up the table and see that the destination EA is on port 4. And so that's what makes that decision. Layer 2 Ethernet switches forward frames based on the destination MAC address. So there are more than one way that you can forward switches. And so one is called store and forward, where the switch waits for the entire frame to arrive. It then does the error checking. So basically it computes the CRC and compares it to the number that arrived in the footer of the frame. If it's the same, it means there's been no errors in transmission, and so it will then make a forwarding decision on that frame. And so it will look at the destination MAC address and then decide which port it needs to be forwarded out of. So that's store and forward. That's the old traditional way that bridges have done it for 30 years. Switches, especially enterprise switches, have another method which is called cut-through switching. And so what that is basically the switch has to wait for the entire destination MAC address to arrive, which is one of the first things in the frame. And so as soon as it's read that, it will then do a table lookup and then start forwarding it. And so there's a lot less latency involved. And so it's a quicker method. Now, with modern networks these days, the number of errors in transmission are pretty low, and so that method does work well. Now, the only hitch for the cut-through system is if maybe you've got some old legacy hubs on the network, or some hosts that don't support full duplex transmission. That would be rare these days. There is actually a compromise between the two. Does it show? All right. So store and forward, basically, as we've said. And then with cut through, again, I've explained it. And then, so does it say? All right. There is actually an option called fragment free. Okay, here it is down here. And so fragment free is modified form of cut through switching, and the switch waits for the collision window, 64 bytes, to pass before forwarding the frame. And so if you remember, I think from CCNA 1, the minimum frame size for Ethernet is 64 bytes. The reason for that is because back in the dark ages when we had bus networks and hubs, that was to make collision detection more reliable. And so all collisions should happen within the first 64 bytes of the frame when it's transmitted. And so having this fragment free where you wait for that first 64 bytes to arrive is basically where it's going to cut down a lot of your errors being retransmitted. And so it's a good sort of compromise. And so it's a little more latency than cut through, but a lot less than store and forward. And so it's a compromise. So collision domains. Now, collisions only happen if you have a bus network or an Ethernet hub. And so they're a non-event these days, thankfully, because you don't see too many hubs about, or bus networks. So in a hub-based Ethernet segment, network devices compete for the medium, therefore collisions will occur. So with hubs and bus networks, only one workstation could transmit at any one time. And so that was, if more than one transmitted at the same time, that was when you got a collision. Now, there were ways to minimize collisions, but in Ethernet, there was never a way to stop them, at least prior to switches. So Ethernet switches operate in full duplex, so collisions are pretty much impossible. And so Ethernet switches will auto-negotiate full duplex if connected to a full duplex device. If connected to a half duplex device, then the port will operate in half duplex and be part of a collision domain. So, but that's each individual switch port, which is better than what a hub was, which was everyone that was on the hub network had to share the bandwidth. So only one station could transmit at a time. So collision domains are much the same as broadcast domains. The smaller they are and the more you have of them, the more efficient a network will be. Now, a broadcast domain is basically one switch or multiple interconnected switches will form a single broadcast domain. So switches don't control broadcasts, only routers do. And so with a broadcast, of course, that's a destination address of all ones, 32 ones, or I suppose if we're talking about MAC address, it's 64 ones, isn't it? It's 48 ones. One switch or multiple interconnected switches form a single broadcast domain. When a switch receives a broadcast, it will forward the frame out each of its ports, all of the ports except for the one it arrived on. When two switches or more switches are connected together, the broadcast domain is increased because the broadcast is propagated from switch to switch to switch. Too many broadcasts can cause network congestion. So again, the smaller the broadcast domain, the better. And so now, broadcast domains are only controlled by routers, and so the solution around that is to you can have multiple VLANs, which is one of the topics coming up, and you can actually have less hosts on the same network at the same time, and so there's less chance of broadcasts. So, how do we alleviate network congestion? So, basically, full duplex links will prevent collisions, and so that slows down a lot of congestion. High port density, so lots of ports available. Large frame buffers, and so basically the switch has a lot of RAM so it can buffer frames. Port speed, the faster they go, the less congestion. Fast internal switching, so that's that backplane where all the data moves between ports. And so, of course, a lower per port cost would be nice. So basically, and so, of course, minimizing broadcasts is another way to improve your network congestion problems. Now, so that's it for the chapter. We're up to the chapter summary. So we've looked at how switch network supports small and medium-sized businesses, and we've looked how layer 2 switches forward data in a small to medium-sized business as well. That's it for the chapter. That's not a big one. The next chapters following on, we will actually get into more depth into the switching side of things.